All right. So good morning, and thanks to the team for the invitation to give this talk. And I have been giving various conference talks, so I know that this is going to be different because the audience is different, the format is different, and you expect something different from me, and that is quite a challenge because I had to prepare this non-scientific talk for an audience who may not be very familiar with the science that we do at the most elementary level. Okay, so to set the tune, I'll be asking you a very simple question that what is antimatter, okay? So just to give you an idea, and I'd also like you to imagine the world where you have abundance of antimatter particle. We know that we are all made of matter particle, like the electron, for example, but we do not see the antimatter particle in our universe. So I think I would like you to imagine today that what happens if you have antimatter particle in the universe. Just to give you an example of what I'm talking about, we see light here, right? In this room, we see that electricity is flowing, the current is flowing in the wires because of which we are getting the light in this room. So the question that we are asking is, why not we have, this is because of the electron flow, the question that we are asking is, why not we have the positron that is flowing in the wires giving us the same current? In fact, in the experimental lab that we do, that we perform in the laboratories, we actually can produce light from the flow of the positron. So that is all we do in the lab, okay? So that is possible. Then the question is, why not in our day-to-day life we do the same thing? And I think that will be a remarkable thing to do, that you produce electricity both from the electron and the positron, so that you have abundance of those energy and the light that you are all deprived of it, at least in this country. Now, when we talk about this antimatter, so I'm talking about this electron that is flowing in this wire to give us a light. That is a real particle that we are talking about today. But we have the same similar particle, which is the positron, which is the oppositely charged particle, the electron. But it has the same properties as the electron, but only the charge is different. So it is a positively charged particle, and we say that is an antimatter particle of the electron. Okay. Now, what has happened is that remarkable things are going to happen, that if you bring a particle and antiparticle together, you will see the energy being produced. So that is what is a process called annihilation process, okay? So, and I think it will be also good for our life because, that is also going to stop the energy problem that we are facing in this world today, because we require a lot of energy to run our world. So if we can have the particle and antiparticle coming in, producing the energy that is required for our day-to-day life, I mean, that will be a wonderful thing to happen, right? But I think be careful, because you can also produce the particle and antiparticle in equal amount from the energy. That is what Einstein told us, that E is equal to mc square equation is true. And that is being seen in experimental facility that we had, or experiment that we have done, that we have an incoming photon coming in, or energy coming in, interacting with the detector, and we produce the electron and the positron there in equal amount. They're spiraling in opposite direction, and from that you can actually find out that they are oppositely charged particle, and that is being experimentally seen. Okay, so these processes are really real process that is happening in our day-to-day life. Okay. Now, if you have those antiparticles, for example, the positrons, for example, if you have that, you also have similarly the antiproton, okay? Then you can make more complex object, for example, the hydrogen. If you can, this is my hydrogen that we are all familiar with, the hydrogen atom. You have the proton inside the nucleus, and you have the electron that revolves around it to form a hydrogen atom, right? That is what we have in this world, and that is what we are familiar with. But I can now do the same thing, that if we have an antiproton at the center of my nucleus, and I can put an anti-electron or a positron around it to form an anti-hydrogen. So that is possible. In fact, we have done that in the lab. So you have an anti-hydrogen, you have formed, which is an antimatter particle of the hydrogen atom. Okay, so that can be done. Now, if you extend that, you can actually make more complex molecules. For example, you can make water molecules now. The water that we drink in the water that we have in the bottle, so it has an H2 molecule, H2O molecule. You have two hydrogen and an oxygen atom. They are being brought together to make an H2O molecule. Now, if you have enough of those anti-hydrogen and also anti-oxygen, then you can bring them together to make anti-water molecule. Okay, so that is again possible, and I think that can be done in the laboratory environment. Now, the question is, now if you keep on doing that, keep on building the heavier and heavier object from those elementary particles, the question that we should be asking is whether we can make an anti-art. Okay, whether it is possible. The art that we have, that we are living in, can we also have an antimatter object of the same art? Okay, in principle, in physics, that actually is a possibility. Okay, so that is a possibility. If that is a possibility, then you should be also asking us yourself that can we have an anti-us, like anti-people, for example, somewhere in the universe, and that is what we need to look for. Now, to understand the importance of what I am talking about, so again, we must have heard about the Big Bang theory in physics. You must have also seen the series or that TV series or the stories there. And so what is a Big Bang? So everything is created from the energy. So there was an initial blast at the time t is equal to 0 when the universe was created, and you can create equal amount of matter and antimatter particle from there. Now the question is that the matter remained today, but this antimatter particle have disappeared. Okay, so that is what we see today. And now, in fact, if you perform experiment in a laboratory, so you actually see an equal amount of matter and antimatter particle. But only in the nature, we don't see them. Okay, so only antimatter particle that we see is only in the laboratory environment. For example, in the lab, so far we have made about 10 to the minus 9 gram of antimatter particle in the laboratory. That's all we have done. We have seen some antihydrogens, some at the European facility called CERN, and at 57 about at Fermi lab, where I actually participate, I conduct experiment. And we have not seen any of those anti-atoms in the cosmic rays, which are coming all the way from the cosmos to us and then hitting us all the time. We don't see them. And of course, we have not seen any evidence for anti-stars, anti-galaxies, and also anti-universe. So the question that we're asking is today is what happened to this antimatter? Because they were produced at the same amount as the matter particle at the time of Big Bang. Now, to understand this missing matter, I think we need to understand what happened after the Big Bang, okay? So when this any time was about 10 to the minus 34 seconds, it was a very hot environment. The temperature was roughly about 10 to the 26 degree. We actually had slightly imbalanced amount of particle over antimatter particle, but this is about 1 in 10 to the power 9 antiparticle. And that number was equal to the number of photons, okay? Now, when the age of the universe became about a second, the temperature was cooling down because the universe was expanding. So then we have seen that all the antiparticles have disappeared from the universe, okay? So basically now if you want to understand something, you have to go back in time to about a second from the time of Big Bang to understand what happened to this antimatter particle. Now, this is what the Big Bang theory tells us, that this is this is time t is equal to 0 when everything got started, and now this is where it was at 1 second. There's all these particles and antiparticles. You can see that they were actually moving in some kind of a quark gluon plasma, some kind of a plasma kind of environment. Okay, and then today we are sitting at 15 billions of years from time t is equal to 0, where everything looks like it is settled. The galaxies are being formed, the planets are being formed, the Earth is being formed, and we are living here and talking in today's TEDx event. All right. Now, to understand this, that what happened to this antimatter particle, now we are building experiment. So this is an experiment in Japan that I am participating in for the last at least 20 decades now, roughly. And this is the Mount Tsukuba where my lab is located. This is the ring, the circle thing that you can see where we are actually accelerating particle and antiparticle, the electron and positron, and we are colliding them to understand or producing this particle called B meson and trying to see whether the particle and antiparticle of B actually behave the same way or they behave different ways. So that is what we are trying to do in this particular experimental facility. You can see this ring where the particles and antiparticles are being accelerated. That is the accelerator there. And this looks like a control room where we control everything from with the computer terminals. And this is a picture that was taken in 2008 when this collaboration was formed. And you can see me sitting at the front there when I was very young and just getting into my academic life at IIT Guwahati. Now, this is an experiment that we have built over the last 15 to 18 years now. This looks very complex, but this is where we are colliding the particle, electron and positron, and trying to see what is coming out. And that is where these particles are being studied to understand what happened to this antimatter particle. Now, we are actually producing this matter and antimatter particle here and trying to understand what happens to this antimatter particle there in this laboratory environment. Okay, so this is a very complex setup, but I'm glad that some of my students are working on it, and they have contributed to some part of the detector development as well. So the paradox that we have today is that the nature seems to choose matter of an antimatter particle, And we see that, in laboratory setup, we also see perfect symmetry between matter and antimatter, except two of them. That's asymmetry that I'm talking about, where particle and antiparticle behave differently, is being found in two decays or two particles of K meson and B meson so far only, nowhere else. Okay. And that is being seen, for example, in a this particular particle. Again, you don't have to understand what is a K meson is or what an anti-K meson is, but you can think of this particle as a particle like an electron, but it's a more complex particle because it has quark inside it. And these two particle and antiparticle, they oscillate back and forth between one kind to another kind. And this is a very rapid oscillation that is happening. This is about 5 billion times per second. That is how fast that oscillation is. Okay. And in 1964, we have found that there is a difference the way this antiparticle goes to a particle and particle goes to antiparticle. So there's a difference in that probability of that oscillation from one flavor to another flavor. And that is being measured to be around 0.23%. Okay, so that is a kind of an experimental evidence that there's a difference in the way the particle and antiparticle behave. Now, similar to that, we have now seen that, again, this is a very complex plot. I think, again, I'm not expecting you to understand it. But then if the world where symmetry for this particular particle B0, then you'll be expecting that the red and then the blue curve is going to overlap. Okay, they should overlap if they're perfectly okay. I mean, they're similar in kind of their behavior. But just because they're not similar, I think that is an indication that the B0 particle and an oppositely charged particle, the B0 bar, they're actually different. And that is another evidence for us to say why these matter and antimatter particle are different. Now, these are big experimental collaborations. So we have about 400 people from 1920s in this BEL2 experiment, and this is now currently operating and taking data. Now, I think that is what we have understood in the quark sector. Now, I think we also need to look at or build another citadel like this to understand or find out another avenue of this CP violation or the matter-antimatter asymmetry. And that is where this experiment is coming up. This is under construction at this time in the US at Fermilab, and this is a project that I'm leading from India at this time. So here in this experiment, we are going to put a detector deep underground, about 1.5 kilometer deep underground. Which is going to be located there about 1,300 kilometers from Fermilab, which is located at Chicago. That's a lab. It's a world-class facility for particle physics. And then we are going to find out how this neutrino particle behave when they travel a distance of, let's say, 1,300 kilometers. I think these neutrino particles are quite interesting particle because, if we travel, for example, for a distance of 1,300 kilometers, we are going to remain us, right? But these particles are not remaining themselves. So I think once they travel that distance, they become something else. Okay, so that is what is called a neutrino oscillation. And that is something that we need to understand because we are going to calculate whether the probability of this particular nu mu going to nu e is the same as the antineutrino version. And that is going to be another clue of understanding why this matter and antimatter particle, in this case the neutrinos, are why they're behaving the way they are. So this is the location, this underground lab, which is getting ready now. This is about 1.5 kilometer deep underground, and this detector is going to be put inside this location. This is, again, you can see the size of this particular facility is about 66-meter detector that is under construction right now. And the other two dimensions are roughly about 12 meter by 16 meter. And that big detector is going to be placed underground 1.2 to 5 kilometers from the top of the surface. And we are going to run this experiment for at least 30 years, starting from 2030. And I'm sure I'm going to retire by the time this experiment is over. Okay, so these are long-term projects, and these are long-term investment that we are doing to understand the physics at the most elementary level. So this is, again, a very big collaboration. There's a lot of people from many countries, including India, and we are working for the last at least 10 years now to get this experiment started and running. Okay, so that is something is going to happen about 10 years from now. So what we have learned. So this is where we were in the beginning of around 1900. And when the electron was discovered, and we found that the nucleus can be broken up, and we can see the proton and neutron inside the nucleus. Okay, that was 1940. And then electron size was also measured. It was roughly about 10 to the minus 16 centimeter. Now, in 1970s, we could actually also look inside the proton and neutron to find out the quarks. Their size is much smaller, it's about 10 to the minus 16 centimeter. Now today we are asking that whether these are the elementary particle that makes everything in this universe, or there are even more elementary to these quarks, whether we can break those quarks to find out even more substructure of those particles. So that is a question that we're asking today. So this quest continues, okay? Now, finally, I think, again, you don't have to understand what this picture is all about, but I think just to make yourself aware that everything that we see in this universe today is actually made of these simple particles that we see on this list, okay? That's all we require to make everything in this universe, okay, the visible universe. But whatever I've talked about today is only going to explain only about 4% of the matter densities in the universe. So 96% of the universe is still unknown. Okay, so that is where the future generation is going to come in, so that you can build your own experiment, imagine or dream your own experiment to understand where this 96% of the universe is coming from, where they are. Okay, we roughly know that there is about 21% is a dark matter. Again, we have some idea about what these dark matters are. They are not seen because they are not interacting with us. But about 74% is what is called a dark energy. Okay, there is nothing known about them. So that is where the future is lying in terms of the research that you can do, the experiment that you can build and set up to understand what happens there with the 21% of the dark matter and 74% of the dark energy. Okay, so because I'm running out of time, so I think I'll stop there and I'll say that keep dreaming and design and build your own citadel so that you can explore the nature at the most elementary level. Okay, thank you so much for your time.